Welcome to Normal Sampling. I'm Jeff Myers, and if you've ever wondered whether sampling equipment, such as this sampling scoop, contribute to sampling error, this is the video for you. So let's get into it.
This is a follow-up to the heterogeneity talk. The heterogeneity is our starting point for sampling and decision making, but even once we conceptualize what the heterogeneity is, then there's actually a big issue about extracting the material correctly, because we can also mess up the sample at that point. You remembered in Piaget's error diagram, the 7 sampling errors, there's increment or sample delineation error and extraction error. So they're 2 separate errors. We'll talk a lot about that here. I'll run you very quickly through a lot of pictures of sampling devices you've probably seen. If not, you can get them on the net. But we will talk about what is the difference between a correct sampling device and an incorrect sampling device, which before I started this, I had no idea there was such a thing as an incorrect or correct sampling device, but it does make a difference. I had some sense, this was actually from my first job. I was a field geologist in East and West Texas, and in West Texas, they have oil. And I came up to a well. We were actually drilling for lignite and subbituminous coal, but I came up to this oil well, and somebody had a little mayonnaise jar or some kind of jar, and I thought, all right, here's Bubba, as they would say in the South where I'm from. He just runs out there, unscrews the thing, dips it in, and he gets a sample. Now oil, well, it's probably more homogeneous, but there are stratification by layers. Okay, so he can bias his sample too. And I didn't know I would use it, years later, but that's an incorrect sampling device. Well, why are we concerned about correct versus incorrect sampling devices? Well, it goes back to an issue that's associated more with laboratories, and that is precision, accuracy, and bias. And this rolls into statistics, of course. We want to define those because precision and accuracy are sometimes a little bit confused. They're sort of related, but they're not the same thing. Basically, the simple way to think of it is precision is how much repeatability do you have. If you can measure a quantity over and over and you get very close to, if not the same answer, that's repeatability. That's precision. Or if you're a marksman, if you shoot at a target and you shoot over and over and you get the bullseye, or you get a tight pattern, that's repeatability. Now, you also have to be careful of what they call the Texas Sharpshooter. There's an old story about the rancher who wanted to increase his income by selling his services as a marksman and a trainer. So he went out to his barn and backed off some distance, shot a bunch of holes in the barn, took a can of spray paint. Guess what? He did a pretty good job hitting the bullseye. Okay. So you have to be careful of that syndrome. You have that a little bit, which we'll talk about. So if she has it, you guys probably have it too, about people kind of, and this is what I said about Mark Twain and lying with statistics. It depends when you ask the question or when you draw the circle. Sometimes that's a big deal. So anyway, it's kind of humorous, but that contrasts with accuracy, which is how close to the real value is the answer that we get, or the answers that we get. Okay? Now, repeatability is easy to measure. Accuracy, it's a lot harder. Why? We never know the true answer. Okay. And so it's a guessing game. As it turns out, and this is not their fault, laboratories can measure repeatability easily, and so they measure inaccuracy, not accuracy, a lot of the times. And they do that not only with instrument repeatability, but by looking at blanks and reference materials and spikes and things like that, duplicates and so on. Now, the bias comes in where, and it's defined as the amount of deviation from the true value. Now, the problem with sampling bias is that we never know if it's high or if it's low. Sometimes if you have a machine that's out of tune or something, you can detect a bias and maybe even adjust possibly in retrospect, saying it was always high, it was always low, or always high in a certain range, or always low in the high range, or whatever. You may have a little bit of compensation there, but in any event, the goal is to have high precision, high accuracy, and low bias. And so my analogy of the Texas Sharpshooter is really kind of how they represent the concept of precision, accuracy, and bias. If we look at this one, we have very high precision, but it's not very accurate. This cluster of bullet holes, so to speak, should be in here. Over here, we're not really very accurate, and we're not very precise either. Okay, we have samples all over the place. Here, precision, not great, and it's not accurate either. And of course, this is what we want. We want very precise data that always represent the true value. This is not so different as the Poisson distribution we saw in the last slide, where the mode and the mean were the same thing. So you had a normal distribution. This is what you want. Things are clustering close to the true value. That's what we were doing in that statistical diagram, that histogram. Here's the context I put that in. We're making an assumption that essentially these are replicates. So this is good, this is not good, because a replicate sample would be all over the board. If this were a representation of the whole site or the whole pile, because you're all over the board, you may find that you got very close to the true value, perhaps by happenstance or luck. But again, it's a different context to ask. This again, where statistics, you have to be very clear what you're doing. Is this repeated samples in a pile or a location in a pile, or is it the entire pile? If this were the entire pile, I would say accuracy would probably improve. It might even be halfway decent. Whereas if this is a single location in the pile, we don't have good accuracy. Okay, so that's a very good question. It all depends on context. Yeah, bias is very difficult to find. Or two, you don't know the sign, typically, of the bias. In sampling, we rarely know the bias. In analysis, sometimes you can find out what the bias is. Or if you happen to have a good reference material and you sample, you can find the bias. And as I mentioned earlier, there are CRMs, certified reference materials for gold. And you test them, and some of them are good and some of them are not so good. So when you compare your process with this reference material, it may say you're doing badly, but it may be their fault. And that doesn't necessarily mean you're doing well, but with others, if it says you're doing well, you really are, and if you're doing badly, you really are too. So bias is tough. Yeah. That's why we try to, we're always going to have some sort of bias. But part of the question is, does it make a difference to our decision making? If your bias is 200%, but your values are both 10 times the action level, I get the picture. It's bad. But if you're near the action level, in fact, that's where you really want the best data. If it's low and you're off a lot, well, who cares? If it's high and you're off, who cares? If you're at that critical decision point, that's when you want the best data possible. Now, correct sampling and incorrect sampling has results that relate to this precision, accuracy, and bias concept. If your sampling structure is correct, you will be certain to get accurate results. That's the theory, and it will prove out. If your structure is good, you will get accurate results. If your structure is incorrect, it is possible, but sometimes it's just by luck. And a lot of times you do get lucky. On the other hand, if your sampling structure is correct, it is impossible to get biased samples. That's good. Or a bias that's meaningful, if that has meaning, significant or substantial, perhaps is a better term. Similarly, or I guess in contrast, if your sampling structure is incorrect, you will probably get a bias. But you won't know the sign, you won't know the magnitude. And that's kind of what the dots diagram was about. You miss it, or you get a cluster and you think you're out of control. Those are both biased a little bit, but you didn't know. I guess you would know if you were biased if you never got anything and you could see it. But you wouldn't know because you wouldn't know what the true value was. Now here are some examples of very common sampling devices, and I'm not necessarily criticizing too badly because we haven't figured out anything better to use, but they all have their problems that we just need to recognize and understand. That, for instance, augers, thieves, and triers, we've got this device where you put it in, you can lose material out of this, and who knows if that's significant or not. Maybe that one had the nugget that you were looking for. The part we know for sure is, well, first of all, you have loss, which is a bias of some sort. Then this little twiddly bit down here, if you go and have the point right at the base, you miss this material in here. Now in a pile, it's possible to have, due to weathering or chemical or bio or whatever, that could be a critical portion that you don't want to miss. In the field, you may have, if you send this below, this point below, and fill it up like to here, this point, this triangle, will collect a bias, dirt that really isn't contaminated. So when you use any of these devices, you can see you're going to get that effect. That's kind of a fact of life. Augers, same thing. Augers are problematic because you have stuff coming from different parts. You know, sometimes you get a little bit more from these higher layers than you do from the base. You have that same problem where you stop above or below. Similar with the triers, you have stuff falling out. It's the same all over. And so I'm not saying don't use them, but just be aware this is going to contribute potentially in some way to what you're using. This is not a pile type device, but the Kalawasa tube is a good example of a correct sampling device. Here you put this tube into, say, a drum typically, and it could have all sorts of nasty stuff in there. You stick it down, you basically close the bottom, you close the top, you pull it out, and you have a sample of the whole thing. Now, that's great. However, you can still mess it up. If it's a fairly viscous liquid and you just kind of slam the tube down, you may have a gap. By the time the Kalawasa tube gets to the bottom of the drum, there may be, say, this much airspace at the top of the Kalawasa tube. So now what happens? Fill from the Okay, so if you have viscous stuff, slowly. Doesn't take that much longer. So even correct devices can be a problem. There's another one, I forget if I have the slide. Yeah, Kemmerer sample depth. This is a correct sampling device. You lower it to the depth in a lake, a stream, whatever. You take the plunger and you go and you cap it, and you get an undisturbed sample of exactly that elevation. Now, there's nothing wrong with this. The problem is it's a pain. You have to do it over and over. It's kind of an expensive deal. So, however, it is correct. They now have something which is really even better, I think. It's only been out a few years. It's called the Aloha Sampler. Guess where it was developed? Hawaii. Yeah. It's really cool. It's just a little jar kind of thing, plastic course, about this big. It's got 2 holes in the cap. And so you submerge it, and basically, typically you tilt it. I'll borrow this a second. This is and this is roughly the size of the sampler. You put it in, it's got a hole here at the bottom, it's got a hole at the top. The water or whatever liquid goes in the bottom, and the air comes out the top. Now it takes about 2 minutes to fill this. That's a good thing, because you might want to say, what's my vertical profile from the bottom of the stream bed up to the top? So you can, over the course of 2 minutes, slowly raise it and get a very representative sample all through that vertical section. Or if you want to do across the stream, you can put these things on a pole, and you could do even a zigzag all the way across the stream. Or if you're in a boat, you can go to different locations. So it's a really cool device, and they've only been out a few years. So again, there are correct sampling devices. Unfortunately, piles don't come in liquid form, so we don't take advantage of that. But just to say that there are correct sampling devices. Now, we mentioned earlier that you might take a large sample in the field and want to do subsampling. And there are different ways to do that. Some are more expensive than others. Some are more accurate than others. Some of the common methods are coning and quartering. The idea is that you make a pile and you cut it into 4 pieces, randomly select one piece, and then either send that to the lab or go through that exercise again, however many times you need. Another one is alternative shoveling, where you take a scoop out of a pile, put it in a little pile, and you do maybe make half a dozen piles. And then you take your die, roll it, you randomly select one of the piles, and that's the one that goes off for the next round of either sub-sampling or sampling. Fractional shoveling, very similar type arrangement. A better way to go are Riffle Splitters. It's a little gizmo. We'll see lots of pictures of these. They have little chutes that for the large ones, and one sends the material this way into a bucket and the other sends material this way into another bucket. And they're all alternating so that if you do it right, again, you can goof this one up too, you get representative samples. Here's the coning and quartering deal. You make a cone with the shovel, you pile it up, then you you flatten it out, you divide it into, these don't look quite equal, but if they were equal, then you randomly select one and go on from there. It's a very simple, very cost-effective way to do things. You have to be careful, as I mentioned, you typically get the large particles around the base of the pile. Alternate shoveling, you make 2 piles, so then you use a coin instead of a die. And fractional, here you make, this says 5, I like 6, but you can use 5. You can use any kind of random scheme to devise your random selection that you like. These are cheap, they're fairly quick. They're not quite as accurate as some of the other ways, but sometimes it works. Now, people often, again, use this technique incorrectly. If you say, well, I'm going to take 5 shovels, and every 5th one I'll put a sample shovel, and then I'll do 4 over here. You don't want to do that. We all have a subconscious bias when we're shoveling. We don't want to admit it, and even if it isn't subconscious, it creeps in there. And so this is a degenerate form. You don't want to do this. If you want to do 4 and 1, or 4 and 1, do 5 piles and then select one. Don't put 4 scoops here and 1 over here. Now, these are on the internet. There's a fellow on our sampling theory LinkedIn site that does a lot of research. He likes to do these simulations. I forget the algorithm, but it's available out there. People think that the solution, oftentimes, to the heterogeneity problem is better mixing and better homogenization. It turns out that's not always true. In fact, it can be the worst thing in the world. There's a thing called a vibratory spatula they use in mining. It's like the perfect segregator. From a sampling device standpoint, you should not use this. Rolling and sifting segregates things, or can. It doesn't always, but it can. So for instance, he's got particles, he's got basically 4 different types. He's got green, white, no, 3. Green, white, and yellow. And here, you can see there's segregation, but there's some degree of mixing. I don't know where it was at time 0, but after a minute, you can see the white ones are starting to segregate here. After a minute, after 2.5 minutes, the white ones are segregating more on the outside. These are segregating here. By the time we're done, the white ones have created almost a lens around this. The green ones are inside that, and the yellow ones are on the very inside. So if you think you've homogenized it, and then you send that to the lab, they're going to probably take the sample off the top, and now we've biased the sample. It's very hard to get a good sample. That's why it's important to know your material to the extent possible. Another effect, and this is what I do with my little models, it's similar, it's called the Brazil nut effect. Especially if you have lightweight particles that are large. I mean, this will happen with a lot of large particles anyway. You start with the nugget down here in several different materials. You start shaking it. And I do have, you can type in the YouTube URL and actually see these things. Kind of interesting. And this thing just starts rising, kind of like rocks in a field. And eventually, after only a minute, it comes up here, and you can see that it rises. And then, actually, in a sense, it homogenized these things, but you still have grouping and segregation down here. Sifting segregation, you can do it that way. You can see here, this tends to send the large particles up and the small particles down. This can be very common. Basically what happens in your cereal box. You get to the bottom of the box of cereal, and the last bowl's got all those little crumbs in it, kind of thing. Very common. And you start here with the thin stuff, or the small stuff on top. Eventually it goes to the bottom, and this stuff comes out on top. The Ruffle Splitter, we'll see better pictures, but conceptually this is what happens. You have a wide pan, tray type of thing. You fill it with material, whatever that you're looking at to analyze. You pour it in. Some of the chutes send it to the left, some send it, to the right, some send it to the left, and you select randomly one of these for subsequent processing. Now, if you pour it in incorrectly, if you don't load the tray correctly, or you somehow angle it so that most goes in one side versus the other, you can get more in one than the other. There will be a bias in this situation. The Riffle Splitter is pretty good because it takes increments from within the shovel. Hopefully there's some representation of the whole going on with that process. A couple things to look for in the design. If you purchase a Riffle Splitter, you don't want the pan to be as big as the receiving bucket, because if the pan is out here, then you get twice as much going in these outside increments. So again, you can goof it up. The receiving bucket, you want it to be big enough so that it takes everything and there's no loss. You don't want loss from the receiving bucket. So here in this particular design, you're getting 5 increments from a single shovel, and 5 over here. Hopefully there's representative sampling going on. Now, when you get to the laboratory, and by the way, the Riffle Splitter is good for the field. They're bulky and they're, take a lot of material. In fact, you probably don't want them in the lab. Rotary splitters are for the laboratory. They're small. They're also very expensive. You need to get your material down to a very small particle size. This little kind of turntable spins around. It's got little holes, and the material drops through, and you get lots of little increments. Very good procedure for taking subsampler. You can have very small riffle splitters for the lab, as the Jones type, as they call it. We got another picture of these. Yeah, there it is. You can see the bucket is very small. You can see that it's about the width of the top. The buckets are a little bit wider than all the chutes, so it's well designed. I can't remember how much these cost, but they're fairly pricey. Also, you can see it's fairly fine material. I thought it would be finer, but it's definitely not field run material. Chuck did another sample on estimating the difference between these various methods. We can see that the cone and quarter approach has standard deviation 5 to 6%. Not too bad, really, overall, considering the sampling error, which itself was 15%. Maximum error, about 20%, roughly. Low cost, that's the advantage. So that fellow we saw with the bucket, that photo we saw earlier, it was actually at Rocky Flats. He could have used cone and quartering or Riffle Splitter or something like that. And even cone and quartering would get him a pretty good standard deviation, a reasonable error, maybe not the best. If we went to a Riffle Splitter, it's a little bit more in cost. Standard deviation drops substantially, the error drops substantially. And at the laboratory, when you go to the rotary, now we're really talking to some money, but the standard deviation goes way down and the error is very low. Depending how much you want to pay, we have ways to do this. Japanese slab cake, very common way to do subsampling. It's both good and bad. The good part is it's simple. The bad part is it tends to bias the samples. You can see that when you reach in with either a scoop or a spatula, as you flatten out the cake, you never get what's at the bottom. You never do. And even though you take all these wonderful increments, you've still biased the sample. That's a problem. Because you can see that it's possible that the big stuff's at the bottom, or it's possible that the fine stuff is at the bottom. You may or may not know. The other problem is that if you use a scoop, like a trowel around a scoop, even if you have it mixed pretty well, you can still get a bias because the scoop will emit this portion of the increment. That's not good. But if you do, especially if you have segregation for whatever reason, you're missing the big stuff down here and you're getting more. A lot of times in environmental stuff, the contamination tends to stick to the clay particles, the finer particles, so you will bias high in that situation. Petard tells of a story of a mining client or mining situation in South America that had an Asian buyer for a mineral. And they would buy big, 40,000 ton shiploads full of whatever this was. And they agreed by contract to sample it by Japanese slab cake. And the Japanese knew of this situation, of the bias. The South Americans, I won't name the country, did not know. And the Japanese would be present for the sampling because it's a big deal because they're paying millions of dollars for this stuff, blah, blah, blah. And they go through the slab cake. They know this is going on and this is their profit, say. And they knew that when they got back, the ship got to dock, they would have about 20% more than the sampling results got. It took a long time for the South Americans to figure this out. And so, is that illegal? No. Is it immoral? It's a little gray. Is it business? Yeah, definitely, definitely business. That's the advantage they had over their competition. So it comes out in odd ways in the real world. The opposite can happen because the spatula works in essentially the reverse manner. Instead of excluding the stuff on the bottom, now you exclude what's on top because you have an angle of repose, you put the spatula in, and the top stuff falls off. If this is your hot stuff, you're losing it. If this is your hot stuff, you're biasing toward that. And so neither the spatula nor the scoop is really the correct sampling device. What you want are things like this: square-walled spatulas, scoops, and shovels. Now, these are very hard to find. You may even have to fabricate them if you are so inclined. But, spatulas, scoops, spoons, common everyday devices. Now, you can go to the store and buy scoops like this. Okay. Well, what do you see? They're not square-walled. They're better, but they're not square. They have this little area between here and the edge that's going to bias toward the top. It's better than a spatula. It's better than a scoop. Okay. So if your material is fine particles, it may not make much difference. But if you have large particles, it probably will. And of course, I've got 3 different sizes. Each of these has a different sample support. So I'm biasing there if I use this versus the big one. All right, got to keep going here. Japanese slab cake, here's another way to do it. You flatten the pile, you send the scoop straight through, get the material, you take several increments, maybe you do it again, second time and get a subsample, and it's a good way to do it. Except it doesn't always come off. Again, you can mess it up when it comes to practice. One thing you don't want is a tray, like a cookie sheet, that has an edge, because you can't get, you got to have that edge away so you get the full scoop. You've got all these little twiddly bits off here. I don't know if they're big, small, whatever, but it's probably not bad. Certainly better than the spatula. But again, the other factor, you know, and what's wrong with this diagram, they have scoops just as I showed you. Better than square walled. They probably had the same problem. I didn't take the time to manufacture my own. But, you know, these are cheap. A few bucks at the store. Lots of pictures here, just some various augers. You can see the type of material impacts basically the tip of the auger. Here's a regular one. You can see sand that tends to fall out. They have a different closing mechanism. Here's for mud. Here's for planer augers. Dutch auger, I've never used one. I'm not really that familiar with that. Flight auger. And you can get kits of these, actually AMS Arts, based in Idaho.
Arts Machine Shop.
Arts Machine Shop.
American Falls.
Right. So, local boy. And I've seen and heard good things about their equipment. I'm not a representative, but they seem to have quality stuff. So, you know, you can get a suite of stuff. They're expensive, but, you know, so is waste disposal. Core sampling, always a bit of a challenge. These are small. In piles, sometimes you'd like a 4-foot core or more. And that's tough. Direct push kind of stuff. Core samplers. You can get longer ones, but they cost more. Shovels, scoops. Sieves are good for field screening. We'll see a couple slides at incremental sampling. Other equipment. Again, kits, arts, riffles, lots of designs. Okay, this will take, you know, huge amounts of material. These are big ones. You see the window scraper. It's a pretty good size device. Another big one, different design. Sometimes they only have one bucket. You really only need one bucket. There's a giant one, a couple of giant ones. Probably don't want that in the lab, but it's also difficult to haul that thing around to the field. Again, the Jones type Riffle splitters. Rotary splitter, that's got a little different design than the one we saw. Some more Riffle splitters. More Riffle splitters. People are very creative. So you can actually go on to the Federal Remediation FRTR Technologies Roundtable. They've got lots of devices if you want to see the latest samples. If you look at SW846, here are some of the sampling devices they recommend. Again, we have the regular versus the mud auger. They look very similar. Sand will be different. Sand, you know, any material, coring is a problem. It's always that end part that you tend to lose. When we were coring coal, we always went into the clay. That helped to keep the coal up in the barrel. But sometimes you lost it. Sand is very hard to keep in there. Clay is hard to get out sometimes. So it's always a challenge. And you know, when you're on a pile, it's very difficult to drive the drill rig up on top of the pile. You have access issues. Whereas if you want to go just out in the field, take your direct push or your drilling rig and go boom, hole goes down, everything comes out. Syringe, these are the Encore type samples. I was actually surprised EPA was okay with this the first time. Volatiles are tough. This probably is a good as good a sampling device as we can come up with. Soils, and different types of soil profilers. Coring devices, you have thin wall tubes, you have split spoons, split barrel samplers, different kinds of tips for augers. You have rotating core devices. This one looks like it's certainly carbide, maybe even diamond impregnated. For rock, if you're going for diamonds, you need diamond drilling. There's only one good scoop right there. Again, the tri-ears and thieves. Bias, but a lot of times that's all we have. So I actually finished early, okay. Precision and accuracy are different. Hopefully our little Texas Sharpshooter type diagrams help to conceptualize visually what the difference is between precision and accuracy. Bias is our tough one, and that's what our task is and our challenge in sampling, is to try and minimize those biases. We've seen that common sampling devices are often incorrect. They have loss of material either from the sides or at the bottom. Sometimes they overtake the actual target material and we get contamination at the very bottom. So it's a problem, and you will have to make your own decisions as to what type of bias you feel is best for your situation. And that's kind of where we are. So again, correct sampling is like the holy grail. But as you can see, it's very difficult to actually make it happen in the field because of logistics. Now, a perfect sampling device really would be a sphere that you could somehow put into the ground or the pile or whatever you're sampling and grab it. I don't even think they make such a thing for water, certainly not for soil. So if you want really an accurate three-dimensional volume, a core sample is probably as well as we can do in particulate materials, say in piles or soils, and that's not bad. But again, the bigger the core, the better the sample. You know, miners, when they're drilling thousands of feet sometimes for gold or whatever, you know, they use 1 and 2 inch core, but you don't get a big picture. It's like looking through a pinhole, okay? And then a lot of times they split that in half. You know, even if you get a 3-inch core, you got a mountain out there. You know, is it really representative? So sometimes it's just plain old luck. Again, we come back to the lab. A lot of times it's not their fault. A lot of times it's the sampling that contributed, and that the most significant errors really came from the sampling procedure. Data are more defensible when we can show that there's a minimum bias in the sampling, design, and implementation, because we know that there's a bias in the sampling device design, and then as we saw in the sampling, and especially the subsampling with the riffles and so on, you can bias in the subsampling stages and the size reduction and the subsampling reduction process too, to diminish the sample support. And EPA supports this. This is in a guidance document by Benjamin Mason. Came out actually way back in 1994. It's in the 2001 or 2, I forget, the RCRA draft sampling guidance document, the one that was delayed. They recommend these types of procedures. And there are others. Now there is a book, not a book, but a guidance document by the ITRC, a good guidance document. We'll talk about that later. So we have more resources than we ever had. And now you have a white paper, so which just kind of scratches the surface. And so Piaget, this is his famous thing. We'll see this again today. Sampling is not gambling, but it can be. The house always wins in Vegas. They didn't build those billion-dollar casinos to be charitable. They will win. In a sense, we always lose because we never have enough time, we never have enough budget, pretty much, and we never have a perfectly correct sampling device to get the exact increment that we need. And so we live with what we get, but hopefully you're starting to get the picture that we can do things better than we have in the past.
Thank you for watching this video on sampling equipment. Be sure to check out our other videos. See you next time on Normal Sampling.